Hello friends, good afternoon and welcome to EduSat Live Lectures. Dear friends, today in Chemical Thermodynamics, we will be talking about free energy and chemical potential. To discuss this topic, we have with us our subject expert, Dr. Shashank Deep. Dr. Shashank Deep is Associate Professor in Department of Chemistry in Indian Institute of Technology, New Delhi. Without further ado, I would like to welcome Sir to our studios and request him to start the lecture. Welcome, sir.
Thank you, Amritpal. A very good afternoon. Um, in previous modules, I have discussed about various thermodynamic parameters and what was the need to introduce those parameters. So we started with first law of thermodynamics, and at that point we introduced terms like internal energy and enthalpy. Those are state functions. When we went to second law of thermodynamics, we introduced terms like free energy. There are two types of free energy, your Gibbs free energy and Sol's free energy. We also introduced the terms like entropy. All these three terms, entropy, free energy, whether you take Gibbs free energy or Helmholtz free energy, was defined to talk about spontaneous nature of a reaction. So till now we have focused only on closed system where composition doesn't changes. But in this lecture I will try to introduce you to a system where composition changes. So there are four equations which we derive based on first and second law of thermodynamics, and those are given here. du is equal to TdS minus PdV, dH is equal to TdS plus VdP, and dA is equal to minus SdT minus PdV, and dG is equal to VdP minus SdT. These are the basis of all the thermodynamic equations. U is your internal energy, H is enthalpy, A is Helmholtz free energy, and G is Gibbs free energy. This equation is valid only for closed system where composition doesn't change and no extra work is done. So according to these equations, we arrive at this part that a spontaneous reaction is a reaction where total entropy of the system plus surrounding will increase. If we try to define a spontaneous process in terms of G, only system, then we can say that G at constant pressure and temperature should decrease for a spontaneous reaction. Then I introduced you with the extra work, and when extra work is involved, which is work other than your PV kind of work, then this equation changes and you get one extra term which is called dWe. So just you write simply that du is equal to TdS minus PdV plus dWe. So all for all these parameters we just add dWe. Now suppose we have a system with variable composition where composition is changing. In that case, those four equations are no longer valid, or we need an extra term which will account for dWe. So for a system with variable composition, we have U is equal to function of S, V and N. So you can see the differences. Now U is a function of N also. Similarly, H is a function of S, P and N, A is a function of V, T and N, G is a function of P, T and N. So if we know that these thermodynamic parameters are function of your composition, how we can write the differential of these parameters. So let's first think about internal energy change. So in that case, U is written as function of S, V and N, and if I try to get differential of U in terms of partial derivative, I can simply write del U by del S at constant V and N ds, del U by del V at constant S and N dV, del U by del N1 SV N2 N3 dN1 plus similar kind of terms you can just add up. Del U by del S at constant V and N is equal to T. So, you can simply write T ds, and del U by del V at constant S and N is equal to minus P. So, you can add minus P dV plus dWe. So, this is the equation which I just showed you when extra work is available. In that case, you simply write du is equal to T ds minus P dV plus dWe. So, if you compare between these two equations, we can simply say del U by del S at constant V and N is equal to T, del U by del V at constant S and N is minus P, whereas dWe is your these terms. So, dWe is del U by del N1 constant SV N2 N3 dN1 plus dot dot dot. Similarly, we can express enthalpy change also. So, now you see, since this is an open system or a closed system with variable n, so we can simply write H is equal to function of S, P and N, and then we can express the differential in terms of partial derivatives. And we know that dH is equal to T ds plus V dP plus dWe. So, from that we can simply get del H by del S at constant P and N is equal to T, and del H by del P at constant S and N is equal to V, del H by del N1 at constant SP N2 N3 dN1 plus this whole term will be equal to dWe. So, when we are calculating internal energy change, we got dWe is equal to this del U by del N1 SB N2 N3 dN1 plus this, and now we got dWe is dH by del N1 SP N2 N3 dN1. Similarly, we can get 4 equations, one for G, when we express G is equal to function of P, T and N, then dW will be equal to del G by del N1 constant T pressure N2 N3 dN1 plus dot dot dot, and A will be when we take A is equal to function of Vtn, then we get dW is this equation. So, we have 4 equations for dW extra, and dW extra is same. So, we can simply write dW extra is equal to your del G by del N1 constant temperature, pressure, composition of other components into dN1 plus dot 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 is equal to del A by del N1 at constant T V N2 N3 dN1 plus dot dot dot, and similarly we can also write partial molar quantities of U and partial molar quantity of H. So, you see these 4 terms are equal to dWe. Now, these 4 terms are equal to dWe, and since the dN2 will be independent term, we can simply write these 4 terms should be equal. So, del G by del N1 dN1 is equal to del A by del N1 dN1, del U by del N1 dN1 and dN1, and you see that dN1 is common. So, you can just cancel out dN1. So, you have this quantity, you have these 4 differential which are equal to each other. All are partial molar derivative, but under different conditions, partial molar derivative under different conditions. These terms are defined as chemical potential. This is defined as chemical potential. So, chemical potential of ith component is equal to partial molar internal energy change at constant S, V and J this is also equal to partial molar enthalpy change under these conditions. This is also equal to partial molar Helmholtz free energy at constant T, V and J, and similarly partial molar Gibbs free energy under constant temperature and J. So, if I put this mu I in place of this derivative, what we will get is these equations: du is equal to Tds minus Pdv plus mu I dni, dh is equal to Tds plus Vdp plus sigma mu I dni, and similarly you get 4 equations, which is basically important equations when you are dealing with chemical reactions or phase changes. You must remember that in chemical reaction or phase changes, the moles of reactant and products are changing. Similarly, in the phase, component of one phase is changing, component of another phase is also changing. So, when this composition changes, we have to take a system, we have to assume that these thermodynamic parameters are function of n also. In that case, chemical potential is very important quantity, and the 4 equations which we get is this 4 equation. Here it is dA. So, please note that here this is dA is equal to minus SdT minus PdV plus mu I dni. So, you got 4 important equations. So, whenever you come across a chemical reaction or phase change or a system where composition changes, you must apply this equation. So, what is the chemical potential change? It is simply del G by del N at constant temperature, pressure and J. This is the most commonly used thing, because you know that most reactions takes place or physical processes, phase changes takes place at constant temperature and pressure. So, most important definition of chemical potential is this, which is partial molar Gibbs free energy at constant temperature, pressure and composition. So, what does this tells you? That chemical potential of a component, chemical potential of ith component is equal to change in Gibbs free energy when 1 mole of that component is added. When 1 mole of that component is added to the solution, keeping temperature, pressure and Nj constant. So, this is typical definition of a chemical potential. Okay. So, if we understand chemical potential, can we define chemical potential, simple chemical potential in terms of simple thermodynamic parameter, not the differential things. So, for that we can simply integrate this equation: du is equal to Tds minus Pdv plus sigma mu I dni. This equation can be integrated. This is from Euler's theorem. This can be integrated because if you see these all parameters u, s, v and n all are extensive parameters. If one of them will be intensive, then you cannot integrate it. So, out of those 4 equations, only this is the equation which is a function of extensive functions, and so it can be integrated. So, Tds, if you integrate du, you will get u, Tds you will get Ts, minus Pdv you will get minus Pv plus sigma mu I ni. And you understand that G is equal to H minus Ts, which is H is simply u plus Pv minus Ts. If I put it here, Pv, Pv cancels out, Ts, Ts cancels out, what you will left with is your G is equal to sigma mu I ni. So, suppose there is a 2 component, then we will write simply G is equal to N1 mu 1 plus N2 mu 2. If we have a 3 component, then we will write G is equal to N1 mu 1 plus N2 mu 2 plus N3 mu 3. So, suppose we are considering phase changes of pure component. This is a single component thing. For example, water is available as ice, water as a liquid form, water as a vapor form. In that case, you have three phases, but component is one. When you have a one component system, you are dealing with one component system, then it is G is equal to simply becomes N into mu, and so mu is equal to G by N. So, chemical potential is nothing but molar Gibbs energy, molar Gibbs energy. So, since chemical potential is equal to molar Gibbs free energy, we know the temperature dependence of G, we know the pressure dependence of G. So, we can know the chemical potential, temperature and pressure dependence of chemical potential. Now, if we take two phases, what are the different kind of equilibria which can exist? Okay. So, think of there are two phases alpha and beta, two phases alpha and beta, and you are taking isolated system. So, constant U and V system, okay, constant U and V system. Suppose temperature is not same for alpha beta phases. So, in that case, we know that equilibrium condition is ds. For isolated system, equilibrium condition is ds at constant u and v is equal to 0. What will the ds? Ds is simply ds for alpha and ds for beta, that is 0 under constant u and v. And ds alpha, so you can think of that if temperature is not same, then your heat will flow from one side to another side. So, suppose heat flows from alpha to beta side. So, here heat is lost, here heat is gained. So, in this case, this way ds alpha will be minus dq by T alpha, where ds beta is dq by T beta. This should be 0, and we know that this dq is equal. So, this gives you condition T alpha is equal to T beta. So, if temperature is not same, heat will flow till T alpha does not become T beta, or temperature of both phases does not become equal, heat will flow from one side to another side, and once temperature is equal, then we achieve equilibrium, and that equilibrium is called thermal equilibrium. Now, if we have a system which is at constant volume and temperature, okay, so we are now not taking isolated system, we are taking a system at constant volume and temperature. We know what is the equilibrium condition, which is del A dA at constant V and T is equal to 0. Okay. So, suppose if we do not have equilibria, then volume will flow from one side to another side. If pressure is not equal, volume will flow from one side to another side, and in that case, suppose dV is the volume, dV is the increase in alpha phase, then the volume change for beta phase will be minus dV. In that case, since you must understand this is the constant volume system, so total change is going to be 0, total change is going to be 0. So, in one phase it changes dV, in another phase it will be minus dV. So, we can simply write P alpha dV minus P beta dV is equal to 0, and that gives you a condition P alpha is equal to P beta. So, volume will flow, volume of one phase will increase at the expense of another phase till pressure does not become equal, and that is known as mechanical equilibrium. So, at constant V and T, the pressure of two phases is going to be same, if not one phase would increase in volume at expense of other. So, this is known as mechanical equilibrium. Now, if I take a system which is where composition changes, So, most common is, and if you take that we are talking about constant temperature and pressure system. So, in that case we have dG at constant temperature and pressure is equal to 0. So, G becomes the criteria for equilibrium, which we have already discussed. So, if we discuss for an open system, we have dG is equal to minus S dt plus B dP plus sigma mu I dNi, and since reaction is taking place at constant temperature and pressure, so we can simply write dG at constant temperature pressure is sigma mu I dNi is equal to 0, and that leads to the chemical potential of alpha phase is equal to chemical potential of beta phase, and this is known as chemical equilibrium. This is known as chemical equilibrium. So, component N will change till chemical potential of that component does not become equal to in each phases. So, chemical potential of ith component in alpha phase is equal to chemical potential of ith component in beta phase. When this becomes equal, only then there will be no reactions, and that is known as chemical equilibrium. So, at constant temperature and pressure, the chemical potential of a component should be the same in two phases. If not, the transfer of that component will take place from one phase to another. So, now we know that there are three different types of equilibria. One is your thermal equilibrium, then mechanical equilibrium, and then we have chemical equilibrium. So, three different. So, for a system to be at equilibrium, all these three equilibria should be attained, then only the system is at equilibrium. So, let us think of what were the various equilibrium conditions which I discussed right now. So, you see this is at constant u and v, your equilibrium condition is T alpha is equal to T beta. At constant v and t, we have P alpha is equal to P beta, whereas at constant P and t, we have your chemical potential of ith component in alpha phase is equal to chemical potential of ith component in beta phase. So, we have three different conditions. First, for isolated system, these all are very common system. First is your isolated system. So, whenever isolated system we are discussing, temperature must be constant at equilibrium. The second is your mechanical equilibrium, or where constant P and V type of system, constant constant V and T type of system. At that point pressure will be equal, and the last is your chemical potential, which is what we generally observe in case of chemical reactions of phase changes. So, what I have discussed in this lecture is, I have introduced a new term which is called chemical potential, and chemical potential is nothing but your change in free energy gives free energy when 1 mole of component is added. 1 mole of component is added. Your G is your sum of G is basically equal to N1 mu 1 plus N2 mu 2 plus N3 mu 3 plus dot dot dot. So, for one component system you have G is equal to simply N mu, and mu is your G by N. So, this is basically molar gives free energy. Molar gives free energy, whereas your if you have a 2 component system, then you have G is equal to N1 mu 1 plus N2 mu 2 plus N3 mu 3. So, 3 component system there will be 3 terms, 4 component system there will be 4 terms. But when we are dealing with open system, then your differential of AUPV you get one extra term which is sigma mu I dni, sigma mu I dni. And so, if we go for equilibrium conditions, which we know that equilibrium condition, there are three different type of equilibrium conditions, one for isolated system, one for constant V and T system, one is for constant P and T system. Since mostly reactions takes place at constant P and T, so we generally use G as a criteria for equilibrium, which is basically dG at constant pressure and temperature is equal to 0. dG at constant pressure at temperature is 0. So, dG is, you know, that minus SdT plus Vdp plus sigma mu I dni, first two terms is 0. So, simply mu I dni is equal to 0 becomes criteria for a spontaneous change. Thank you. So, just I defined chemical potential. Chemical potential most commonly is defined as change in Gibbs free energy when 1 mole of component is added at constant temperature, pressure, and if you keep other things constant. This is the chemical potential change. And I also discussed that how your chemical potential of component must be equal in each phases for equilibrium to be established. Now, what I am going to discuss is what happens when a spontaneous reaction takes place. A spontaneous reaction, for a spontaneous reaction, we know that dG at constant temperature and pressure is less than equal to 0, less than equal to 0. So, since most of the reaction takes place at constant temperature and pressure, and so first I am going to discuss the spontaneous reaction at constant temperature and pressure. Okay. For that, your condition is dG at constant temperature and pressure should be less than equal to 0. At constant temperature and pressure, what you are left with is simply dG equal to sigma mu I dni, and since I am just taking only two phases, so I am going to write dG as mu I alpha dni minus mu I beta dni less than equal to 0, where mu I alpha is your chemical potential of ith component in alpha phase, where dni is change in component of 1 in alpha phase. Okay. So, you see that your component is going from beta to alpha. So, number of mole of alpha is increasing, where number of mole of beta is decreasing. Now, you see when we talk about beta, what we have got is mu I beta. Now, we are taking minus dni, since we know that the component I is moving from beta to alpha. So, change will be minus dni, and so the equation we have is mu I alpha dni minus mu I beta dni less than equal to 0. Now, you see that dni you can take as common, and since dni is not equal to 0, we can simply write mu I alpha minus mu I beta is less than equal to 0, and so mu I alpha is less than equal to mu I beta. What does that mean is mu I alpha. So, chemical potential of ith component in alpha phase is less than your chemical potential of that component in beta phase. So, it means that you are going from higher chemical potential side to lower chemical potential side. So, what does that mean is a species diffuses spontaneously from the phase where its chemical potential is higher to a phase where its chemical potential is lower. So, for example, if you want a body to spontaneously move, then what you do is you put at the top, and then top to bottom it will come spontaneously. Top to bottom flow will be spontaneous, but bottom to top flow will not be spontaneous. So, this analogy is similar to what we see in chemical potential, that higher chemical potential to lower chemical potential is a spontaneous process, whereas lower chemical potential to higher chemical potential is not a spontaneous process. So, what is the meaning of chemical potential? It is tendency of a system to give particle, tendency of a system to give particle. Higher potential means more tendency to go to product, or more tendency to give particles, more tendency to change. So, it will like to go from higher potential to lower potential thing. So, suppose a reaction is spontaneous, we know for reaction to be spontaneous, chemical potential should decrease, chemical potential should decrease. So, if suppose the reaction is not spontaneous, then how we can make that reaction spontaneous? As we know that chemical your free energy is related to temperature and pressure. We can change free energy by changing temperature and pressure. Similarly, we can change chemical potential by changing temperature and pressure. And the way we see is, again we will go back to same thermodynamic equation, dG is minus SdT plus VdP, dG is minus SdT by plus VdP, and del G by del T at constant pressure is equal to minus S. Del G by del T at constant pressure is equal to minus S. So, we can change that G by changing the temperature. Now, we know that your chemical potential for one component is simply equal to molar Gibbs free energy change. So, we can also know how chemical potential of one component system changes with temperature, and the equation is simply del G m by del T at constant pressure is equal to minus S m. So, you understand that this G m is nothing but mu. So, differential of chemical potential with respect to T is equal to minus S m. Since S is always positive, always greater than 0, so S m is positive, and so minus S m is negative. What does this tells you is that chemical potential decreases on increase in temperature. Chemical potential of any substance decreases on increase in temperature, since this is negative quantity. Now, think about phase changes, solid to liquid to vapor, solid to liquid to vapor. This is same thing which I discussed, that your one component system, for one component system mu is equal to G by N, and that is why we defined in the last this thing, that your Gm is equal to chemical potential, and we showed that on increase in temperature chemical potential decreases. Okay, so let us think about simple solid to liquid to gas change, solid to liquid to gas conversion. Okay. At 0 degree Celsius, at low temperature, solid is your most stable phase. Solid is your most stable phase. So, chemical potential of solid is lowest. Chemical potential of solid is lowest at very low temperature. Chemical potential of liquid and gas is higher than chemical potential of solid. But what happens when we increase the temperature? When we increase the temperature, we know that chemical potential of each component will decrease, and since this is your negative quantity, but decrease will be more steep for gas compared to liquid and solid. Compared to liquid, since we know that entropy of gas is always greater than entropy of liquid, and entropy of liquid is greater than entropy of solid. So, steepest fall in chemical potential will happen for gas, and then for liquid, and finally for solid. So, you see that solid is decreasing, liquid is decreasing much faster, liquid chemical potential of liquid is decreasing much faster, and there will be a temperature at which chemical potential of liquid will become lower than chemical potential of solid, and this temperature is called freezing temperature or melting temperature. Similarly, there will be a temperature where gas will cross solid and liquid, and then what you will get is what we get is only gas will become the stable phase, and that temperature is called boiling temperature. That temperature is called boiling point, and that is why at the lower temperature you have a solid. Once you again increase the temperature, first it will go to liquid and then it will go to gas, liquid then it will go to gas. Sometime what happens that a substance sublime, for example ammonium chloride, iodine, camphor, what happens in that case is before liquid can cross chemical potential of liquid, chemical potential of liquid becomes lower than chemical potential of solid, chemical potential of gas becomes smaller than chemical potential of solid. In that case your substance will sublime, in that case your substance will sublime. This is simply used, so this is temperature effect. Now you think about when we want to slide, what we generally do, we put the kind of shoe which has blade. Now what is the purpose of that? The purpose of that is to introduce pressure, and pressure will melt the ice. Water between blade and ice is what we really glide across. So chemical potential can also be changed by applying pressure, and this is the one of the most well known case of application of pressure on your chemical potential. So now you see that how pressure can affect your chemical potential. Again same equation, dG is equal to VdP minus SdT. So del G by del V will be equal to, del G by del P will equal to V, and since for one component system Gm is equal to a molar gas free energy is equal to chemical potential. So what we are going to look at is how pressure changes Gm or chemical potential of a component. So we have simple equation del mu by del P at constant T is equal to Vm. Again volume is going to be positive, and so what we expect is chemical potential will increase with change in pressure. Chemical potential will increase with change in pressure. Now question is, we have two components, solid and liquid. So you see this is your solid and this is your liquid. So if I apply pressure, what will happen? Chemical potential will increase for solid, chemical potential will increase for your liquid. How does it affect your melting temperature, that is what we are going to discuss here. Now, you see this Vm is small, solid Vm is small, liquid Vm is greater. If that happens, what will happen? You can see that this Tf shifted to Tf dash. What does that mean? Is there is increase in freezing point. There is increase in freezing point, and that is the general case which we observe for any solid. But water is different. For water, Vm of solid is greater than Vm of liquid. And so, what happens that the increase in chemical potential when we change the pressure will be greater for solid compared to liquid, and that leads to depression in freezing point, and that is why you see that we are able to glide across. Okay, so what does that mean is we can shift equilibrium. So, we can shift equilibrium pressure, we can shift equilibrium temperature, and the way we do is that is what we are going to discuss now. Okay. So, suppose generally if you take water, its freezing point is 0 degrees Celsius, right? Freezing point is 0 degrees Celsius, its boiling point is 100 degrees Celsius. So, suppose I want to increase the boiling point. We want to increase the boiling point, means equilibrium temperature. So, what we should do? We should change the pressure. In which direction? That is what we are going to discuss. If we want to decrease the freezing point, what we should do? Again, we can do that by changing the pressure. Similarly, we have like, if we want to change the equilibrium pressure, we can change it by changing the temperature. So, what is the equation which governs this process? So, suppose we take solid liquid equilibria, okay? And let us assume that at pressure P1 the melting temperature is T1. So, there is an equilibrium at pressure P1 T1. Okay. So, at that temperature and pressure we should have chemical potential of solid is equal to chemical potential of liquid. Now, if I want to change the boiling temperature we now need a different equilibrium temperature. Okay. So, suppose we want our liquid to boil at 120 degrees Celsius, so certainly we have to change the pressure. So, it will no longer be P1. Suppose at T1 or at the temperature 120 degrees Celsius, your pressure is P2, then only it changes to P2 is the pressure at which your boiling temperature is T2. In that case, at that pressure and temperature P2 and T2, we have chemical potential again becomes equal. So, chemical potential of that component in solid phase will be equal to chemical potential of that component in liquid phase. Okay. Since pressure changes, chemical potential has changed, it has become equal, it has become different from mu s, and that is why we are writing for this mu s, this for mu s dash. But chemical potential of solid and liquid is equal at that temperature and pressure. Again at T2 and P2 chemical potential of solid equals. So, if I suppose deduct this, then what you will get? Mu s dash minus mu s is equal to mu l dash minus mu l, and this is what is known as d mu s is equal to d mu l. D mu s is equal to d mu l. So, between two different set of conditions for equilibria, we have d mu s is equal to d mu l, and that leads to what is known as Clapeyron equation. So, d mu s is equal to d mu L, and we know that this is d mu is your dg at dg for one component system. We can simply write this as minus ss dt plus vs dp is equal to minus sl dt plus vl dp. So, s basically here denotes solid and this L denotes your liquid. And so, if we just manipulate this, bring SL this side, take this Vs this side, we will get SL minus SS is equal to dt is equal to VL minus Vs dp. So, we can calculate dp by dt, and dp by dt is equal to del S by del V. So, this is very important equation which describes how phase changes, or what is known as phase diagram, which is basically nothing but pressure versus temperature diagram. Okay. Now, let us think of this is same thing. So, this is equilibrium. So, this is your line, solid this side, phase alpha, phase beta. So, there is equilibrium between phase alpha and phase beta. Okay. At particular temperature, this is the pressure at which equilibrium exists. Okay. And this is your, if I change the pressure for this much amount, here is the point, here is the temperature at which equilibrium will exist. So, there is a relationship between dp and this dt, and that is what I gave you, dp by dt is equal to delta S by delta V. Now, think of solid liquid boundary, okay, and this is the phase changes. So, phase diagram, which is pressure versus temperature diagram. So, dp by dt, if I take solid to liquid thing, del S is what? Del S is delta H by T, and so you have delta H by T delta V. So, suppose I want to change liquid to solid to liquid, then what I need to do? I need to supply heat, and so delta H is positive. Delta H is positive. Okay. What about delta V? We are going to solid to liquid. You must remember that solid to liquid delta V again will be positive, some small. So, this is positive divided by positive is a positive quantity. What does that mean? Is equilibrium pressure will increase if we change the temperature, if we increase the temperature. If we increase the temperature, your equilibrium pressure will also increase, or just opposite way, if we increase the pressure, then temperature will also increase, equilibrium temperature will also increase. So, this is a positive slope. This is generally true for any solid liquid thing. There are exceptions, and one of the most common exception is your water ice system. Since for ice to liquid water, delta V is, ice to liquid water delta V is negative. So, dp by dt will be negative, and you will have a negative slope for P to P versus T graph, which is your phase diagram. Okay, for liquid and liquid vapor boundary, what we will get is dp by dt is delta H by T delta V. Again, we think of this liquid changing to vapor. So, we need to supply heat, and so delta H is positive, delta V is also positive. Generally, volume of gas is always much greater than your volume of liquid, and so it is positive. We will get a positive, but a small value, since this is large, and so this kind of slope will be obtained. This kind of slope will be obtained, and this kind of slope will be obtained. This will be positive, which means that equilibrium pressure will increase if we increase the temperature, or similarly, if we increase the pressure, equilibrium temperature will also increase. Okay. Now, Just try to modify this equation. We know that delta V gas vapor is equal to, is almost we can take as V of gas. Since V of gas is much greater than V of liquid, so delta V is V gas minus V liquid. Since V gas is quite large than V liquid, so delta V can be written as simply Vm gas. And in that case, if I assume that gas is, your vapor is an ideal, behaves as an ideal gas, we can simply write dP by dt is equal to delta H by T RT by P, and then we get dP by P is equal to d log P by dt is equal to delta H by RT square. This is well known Clausius-Clapeyron equation. This is well known Clausius-Clapeyron equation, and by integrating this we can know how vapor pressure changes with temperature. So, now since we have discussed all these things, only one thing is left is solid vapor boundary. For solid vapor boundary, dP by dt is delta H sublimation into T delta V, and we know that this is positive large, so this is steeper than liquid vapor. So, now we understand how your phase diagram of a one component system should look like. Now, this is, you see solid to liquid thing, and you will see that there is a steep, this is positive increase, and then you have this liquid to vapor, and this is solid to vapor thing. This point where all three phases coexist is known as triple point pressure, triple point, and this pressure is called triple point pressure, this temperature is called triple point temperature. At this point you have a critical temperature and pressure, so you have a critical, greater than this is a critical temperature, and your component will exist as supercritical fluid. This is generally 1 atmosphere, it means solid is going to liquid. If I increase the temperature, solid will go first to liquid and then to gas. Suppose you are at pressure which is smaller than this triple point pressure, what will happen is, if you increase the temperature, it will not go to liquid, it will simply sublimes. Solid directly goes to gas vapor. So, what we have seen is that we can increase the boiling point of water if pressure above water is increased. So, just look at these equations, last equation. Here we can change, by changing the pressure we can change the temperature, and from this you can see that if we increase the temperature, we increase the temperature, pressure will increase, and so that is what we do here, that by increasing the pressure you can increase the boiling point of water, and if you lower the pressure you can decrease the boiling point of water. This explains why water boils at 70 degrees C up in the Himalaya. So, you see that pressure at the top will decrease, and so your boiling point will decrease. Now, again elevation of boiling point. You see what we do in pressure cooker is simply you are applying pressure, so that boiling point of water increases. So, you can increase the boiling point of water more than 100 degrees Celsius, you can go till 120 degrees Celsius, and food cooks quicker at higher temperature. This is your Clausius-Clapeyron equation. So, you see that if this is positive, pressure is positive, then T2 minus T1 should be, T2 minus T1 will be positive, and so you can increase the boiling temperature by increasing the pressure. And last, these autoclaves are generally used to kill bacteria. For killing bacteria requires boiling point of water more than 100 degrees Celsius, and so autoclave uses higher pressure to increase the boiling point to greater than 120 degrees Celsius, at which your all bacteria will be killed. Thank you.
On that note, I would like to thank sir for this very enriching discussion, and thank you dear friends for watching our show. Stay tuned and keep watching. Thank you.